Okay, g'day all and welcome to another video. Today we're going to be talking about computing things, but not just anything. Today we are talking about computing everything. The topic of today is going to be an adventure through the amazing world of discrete maths. We're going to time travel through the Victorian era and talk about some crazy ideas that a fella called George had once. And we're going to travel through the 1940s and meet a brilliant little fella called Alan. And we're going to look at how to compute every single thing ever along the way. It's going to be fun. Okay, I have written a little ebook for this video and I'll be putting that up for the Patreon. So as a big thank you for supporting the channel. It really does mean a lot to me. If you, humble viewer, would like to become a Patreon of this very channel, there will be a link down below and another one up above. Okay, that's good. But computing things. Let's imagine that we've got a very tiny computer. It's extremely tiny, so small that a lot of people wouldn't even regard this as a computer, but I tell you what it is, it's just our tiny computer and it's brilliant. Anyway, our tiny computer is very excellent and it reads only 2 inputs and it produces 1 output. For its inputs, they're both going to be binary and its output is also going to be binary. So you could think of this like a computer and it just has 2 buttons, A and B. They're either pushed or they're not. And it's also got a monitor, but the monitor is kind of a rubbish resolution and this monitor is either on or off. The monitor just shows a 1 or a 0. So if we've got our little computer here and the inputs are labeled A and B, then these are all 4 possible inputs that we could give to our computer. These are the questions that we could ask this little computer. Now there is no more. We're either pushing button A or we're not. We're pushing button B or we're not. It's either off, 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 on, off, or on. That's all there is. Now for each of those questions or input patterns, the computer can answer either 0 or 1. It just puts it up on its monitor, 0 or 1. We could add another little column just here for our little computer specification, the output. And this is going to list the answers to each of the questions. So let's define what the answers to each of the questions is. We can just make this up as we go. Well, I happen to like 1000. So let's define that as the output, shall we? Now, some of you, possibly a lot of you, might recognize exactly what this little bad boy is, but keep stum. Okay, but that is our inputs and our outputs. So when we input 00 to our computer, it returns 0. And if we input 01 or 10, our little computer will also return 0 and 0. But, and the exciting bit, I use the word exciting quite loosely, but the exciting bit is when we input 11 to our tiny computer, it returns 1. Good stuff. Now, a lot of you are probably thinking, well, that's the dumbest computer I've ever seen. Who would ever use a computer like this? But what if I was to tell you that this little operation just here is computed literally billions of times per second by basically every single computer on Earth? For this humble little operation is none other than Boolean and. Well, there you go. Mr. George Boole was a mathematician from Victorian era England. Largely self-taught, he defined a logical algebra, which bears his name to this very day. Really quite amazing what this man thought of. Like we're talking, you know, a good 100 years or so before computers really existed. We're talking like Sherlock Holmes days. You know, this is Jack the Ripper era. People were still getting around with horses and carts. I mean, there was barely any electric lighting. He sat down one morning with his cup of tea and just thought, you know what, I'm tired of doing algebra with numbers. I'm going to do it with some logic instead. How's about that? Everybody around him must have just looked at him and thought, what on earth are you, George, what are you talking about? What are you doing? Well, it turns out that Mr. Boole was onto something. I tell you what, the dude was onto something. Holy macaroni. Another fella, Charles Babbage, was going absolutely ballistic, making crazy machines to do just incredible things. He had a machine called the difference engine, was performing calculus with a bunch of valves and tubes and craziness. But anyway, a lot of the ideas that these Victorian era mathematicians, your Booles and your Babbages, a lot of their ideas actually went on to be extremely useful and form the foundation of modern computing. What a history we have here on Earth, eh? What an amazing place. Amazing time. Victorian era. Good stuff. Well done, the lot of yous. So this is Boolean AND. It takes 2 bits of input, A and B, and it returns a single output, O. And the output is 0 for all of the combinations of inputs except where A and B are 1. And the way that we've drawn this out in columns like this actually has a name. This is called a truth table. Truth tables are a common way to specify logical operations such as Boolean AND. Anyway, for George Boole, AND was not enough. for his algebra, so he defined a couple more operations. We've also got Boolean OR, and we've got Boolean NOT as well. And here's Boolean OR. Takes 2 bits, just like Boolean AND. It returns 1 bit, the output column just here. And the pattern of zeros and ones that it returns is different. So that's really what defines these different operations. It's the output. At any rate, Boolean OR returns a 1 for all of the input patterns except for the first one. Whenever the inputs are 0, 0, Boolean OR returns 0. Otherwise, it returns 1. We can think about this in a whole bunch of different ways. Really, the operation is asking, is A or B 1? And if either of them is 1 or both of them are 1, then the answer is 1 or yes or true. And if both of the inputs are 0 or false, then the answer is false. Boolean OR. And the final operation that Mr. Boole defined is Boolean NOT. NOT actually only takes 1 input, and it just returns whatever the opposite is. So if we've got A as our input, if A is 0, then not A is 1. A is 1, then not A is 0. So Boolean NOT is sometimes called the complement, or the bitwise complement, sometimes also called the ones complement. It just depends on the circumstance, but Boolean NOT just flips the bit. I want to also mention that sometimes along with calling these things operations or functions or whatever, you'll often see them called gates, especially when they're implemented in hardware using transistors and electricery. Yeah, logic gate, logic operation, Boolean operation, whatever you want to call it, it's all the same thing. But we've got our 3 Boolean operations here, Boolean AND, Boolean OR, and Boolean NOT. You might be tempted to ask something like, why those 3 operations? Why those 3, AND, OR, and NOT? I mean, they seem interesting enough, but why those 3? You might also be tempted to ask, well, if those 3 exist, how many other operations are there? And what we can do here to figure out the answer to this, we can say, well, the output column has 4 bits in it. And if each of these operations is defined by a different output pattern, then that means that there must be 2 to the power of 4 different patterns, 16 different operations. And here they all are, in all their glory, all 16 binary operations. Would you look at that? Now, it looks a little bit messy. I mean, there's just a bunch of ones and zeros everywhere, but there should be some familiar faces in there. So right here, that's Boolean AND, and here's Boolean OR. You'll also notice that some of these operations have redundant information in them. For instance, the operation not A, just here, which produces the opposite of the A input. Well, not A actually only reads A. Doesn't read the B variable at all. And not B is the sort of reverse of that. Not B returns the opposite of the B variable, and it doesn't read the A variable at all. The first operation just here doesn't even read the inputs, it just writes 0 to the output. And the final operation just writes 1 regardless of the input. Anyway, let's have a look at the first operation, shall we? So the first operation returns 0 no matter what we input. But if we just remember back to what Boolean AND does, Boolean AND returns a 1 only if both of the inputs, A and B, are 1. Otherwise it returns a 0. So what we might do is something a little bit interesting. We might say A and not A. We're performing a Boolean AND with the complement of the same variable. And what's going to happen if we do that? Well, if the variable A is set to 0, then not A will be 1, and we'll end up with 0 and 1. The AND operation will return 0. Likewise, if the A variable is 1 to begin with, then 1 and its complement, 0, is also 0. So regardless of what the value of the input is, if we perform A and not A, we're going to get 0 as the output, no matter what. We've got a sequence of these little Boolean operations that we can perform, and we can emulate the 0 gate. Let's have a look at the final gate. So the final gate writes 1 no matter what the inputs are. Let's have a go at creating that using the Boolean operations. What we can do is we can say A or not A. If we remember back to the OR gate, it returns 1 for all situations except for the input 0, 0. If we OR A with the complement of itself, it's either going to be 0 or 1, or if A was 1, it's going to be 1 or 0. But either way, we're going to get 1 as a result. A or not A returns 1 no matter what. It emulates this final gate, this 1 gate. And so you might have a bit of an inkling of where we're going just here. Those 3 Boolean operations, believe it or not, can emulate all 16 of this complete set of operations. And it looks a little bit messy, but here is an example of how we might emulate each of the 16 gates. You don't need to implement all 16 of the original complete set of gates. You can just implement the Boolean operations and or and not, and you know that you can generate all 16 of the other gates. Okay, but let's be a little bit serious here for a moment. So our computer has 2 bits of RAM and a monitor that's either on or off. That's not very useful. Let's move up to a computer with 3 inputs, A, B, and C. We've got 8 rows now in our truth table, and we can define our little 3 input operation. Once again, if we're talking about binary just here, the output values just here can each be 0 or 1. Just make up a gate while we go. We got, all right, the output column might be for 0, 0, 0. The output might be 0. For the input 0, 0, 1, the output might be 0. Then it might output a 1 and a 1 and a 1 and a 0 and a 0 and a 1. Whatever. We've got some gate just here. And now using this truth table here, we could figure out what our little computer is going to return given any input pattern. Anyway, let's make another gate, shall we? That first one was so much fun. 1, 0, 0, 0, 1, 1, 1, 0. There's another gate. Good stuff. Just by changing the pattern of bits in the output column, we get a new gate every time. What fun. But you might be tempted to ask, how many of these 3 input gates are there? Well, you can see from the output column that there's 8 bits. And if there's 8 different bits, then 2 to the power 8 gives you 256. Pretty crazy. We went from the 2 input set of operations, there's only 16 of them. We added 1 more input, we've suddenly got 256. Now it would seem that these 3 input gates are far too numerous for something so simple as Boolean operations to emulate. But let's have a look at an interesting technique. If we look at this gate just here, we could actually split it into 2 halves, the upper half and the lower half. If we look at the upper half just by itself, and we take away the A variable, we just imagine it doesn't exist for a moment. If we look at this upper half, what we can see is that we've actually got one of the original 16 gates. I mean, this is a 2 input gate with 1 output. The inputs here happen to be B and C, but it doesn't really matter to a Boolean operation. I mean, it doesn't care what the variables are called. And we could do the same with the lower half. If we just ignore the A variable for a moment, what we've got here is a little 2 input single output gate. We've got these 2 halves, and we know that the Boolean operations can emulate both of these halves separately. So what we really want to do is say something like, if the A variable is 0, in other words, if it's the upper half, then you want to use this first expression as the answer. And then you want to say, if the A variable is 1, then we want to use this second lower half as the answer. We need an if statement. But we're in Boolean algebra. We don't have an if statement. What we've got is Boolean AND to the rescue. And what we do is this. For the upper half, we AND that upper half with not A. We only want that upper half to apply when the A variable is 0, or in other words, when not A is 1. Likewise, for the lower half, we only want that half to apply when the A variable is 1. So we can AND that lower half with A. And what we end up with is 2 expressions. We've got not A and the upper half, and we've got A and the lower half. And if we OR those 2 expressions together, wouldn't you know it, we've actually emulated a 3 input gate using nothing but Boolean operations. And what's interesting about that technique is that it wouldn't matter what the bit pattern is in the 3 input gate. It doesn't matter. Any of the 256 different 3 input gates, we know for certain that we could split them in halves. We could AND the upper half with not A, the lower half with A, and we could OR those 2 together. And we would have the 3 input gate. This is really where we start to see just how powerful this algebra is, just how good Mr. Boole's operations were. I mean, you can start to read these as little numbers. I mean, 0, 1, 0, that's binary for the number 2. 0, 1, 1 is binary for the number 3. You could read those as numbers, and we've got gates here, like this one just here. This actually tells you if a number is prime or not. It's an interesting gate. This gate just here tells you if a number is divisible by 3. There's all sorts of questions that these gates answer. But no matter what the question is, any input that can be mapped to the range 0 to 7, we can emulate it with Boolean operations. Now, of course, the interesting part is that we could actually take this further. Let's say that we had 4 inputs. Now, if we've got 4 inputs, A, B, C, and D, and a single output column, or even if we've got more than 1 output column, it doesn't really matter. You write as many outputs as you want. If we've got 4 inputs, there's a total of 16 different rows in the truth table. And if we want to ask a question like, well, how many different gates are there like that take 4 inputs and return a single output? Well, the answer is 2 to the power of 16. I mean, 65536, I think. 65,536 gates of this size. And it might seem a little bit absurd to try and emulate that with Boolean algebra, but we know that we can emulate all of the 3 input gates just by splitting the output column into upper and lower halves. And we could actually apply exactly the same logic here. We could split the upper and lower halves. We know that we can generate each of these halves, and we can actually mask then with the b variable this time, just as we did with the a variable previously. And then we could mask again with the a variable. And what we'd have is rather a long and very messy and complicated looking expression, but we know that no matter what the output column is, doesn't matter how complicated those bit patterns are, we know that we can emulate that 4 input gate using nothing but Boolean operations. And then we can move up to 5 inputs and 10 inputs and 1,000 inputs, 1,000,000 inputs. It wouldn't matter. It doesn't matter how complicated the input is or how long the output column is, we know for 100% certainty that we could emulate that using nothing but Boolean operations. And that's quite profound, really. That's absolutely extraordinary, because it means that no matter what questions we ask, no matter how complicated the questions are, or how many outputs we need, we know for 100% certainty that we could, at least in theory, compute the result using and, or, and not. Now, it mightn't seem that strange to a programmer, but if you think about it, that is quite odd. We've got no if statements, we've got no functions, no objects. I mean, there's no branching or loops of any kind required. We just read the input, perform exactly the same set of steps. There exists some Boolean algebra that will give us the right answer. It means that Boolean algebra is universal. It's complete. There's not a single finite question that we couldn't answer using Boolean algebra. Not one. That really is something. I tell you what, things are about to get even crazier. I mean, they're going to get crazier. Let's have a look at another little operation way back when we were looking at the original operations. There's a gate just here, a funny little gate, a strange gate. It returns the opposite of and. It returns not and. In other words, NAND for short. Just like an and then you not the result. And it's a strange gate because let's have a bit of a look at something. If we go a, NAND, a, if we input the same variable for both parameters, then it's either going to be 0, 0 as the input or 1, 1 as the input. For NAND, if we input 0, 0, it returns 1. And if we input 1, 1, NAND returns 0. If we NAND a variable with itself, performs a Boolean not. But that's just a start, my friends, because have a look at this. NAND is not and, right? It's not and, it's NAND. It's great. If we NAND A and B together, and then we NAND that result with itself, what we'll get is the not of the not and. We'll get Boolean and. We can perform Boolean not and Boolean and using a single weird little gate. Here's an interesting fact. If you take a truth table that's output from some Boolean expression, if you complement each of the inputs, so wherever the variables are clean, you put a not beside them, like A becomes not A, and wherever there's a not, you get rid of it. If you complement each of the variables to this Boolean expression, then the truth table of this function will actually be the reverse of the original truth table. It will be the same thing flipped upside down. If we look at the NAND gate's output, we've got 1, 1, 1, 0. This is what the OR gate returns, but it's upside down. So, if you wanted to emulate Boolean OR using nothing but NAND, all you would have to do is complement the two inputs, A and B. And we know already that we can complement the inputs using nothing but NAND. If we go A, NAND A, NAND B, NAND B, wouldn't you know it, we've got Boolean OR. Now that's a little bit strange. The original Boolean set is universal. You can compute literally anything at all, be it an operating system, a video game, a weather forecast, it doesn't matter, anything at all. But you can compute the original Boolean set of operations using nothing but NAND. And what does that mean? Well, it means that NAND itself is universal. Can compute absolutely anything. You don't need any loops, you don't need any objects, no if statements. All you need is a long string of NAND. This is often implemented in transistors, in CPUs and various other hardware themselves. I mean, this is how computers work. This is how they work. Absolutely astonishing stuff. Shout out to NOR as well. The NOR gate is also universal. Different expressions, of course, to produce the various Boolean operations, but NOR is also universal. I should mention at some point that it's not even remotely practical to use Nand to write something like an operating system, for example. Or if you wanted to write a video game, the number of Nands in your code, if you write code like this, I mean, it would be absolutely astronomically large. I mean, we're not even talking millions or billions here. It would be like a Googleplex or like Graham's number or something. You know, these are completely and utterly impractical. But it is interesting to see that, at least in theory, no matter what the input bit patterns are, and no matter what output you need nothing other than NAND to generate that output. Okay, and so we can't talk about a lot of this stuff without mentioning the incredible Mr. Alan Turing. Really one of the most magnificent people ever to walk the earth. Just an astonishingly intelligent man. Of course, his life was really cut quite short with terrible tragedy, but his work and influence survives today in a very, very big way. So Alan Turing really wrote the book on what it means to compute things. And he envisaged these machines, I think he called them automatons at the time, but they came to be known as Turing machines. And what he said was if you had a tape and there was a head that was reading and writing to the tape, zeros and ones, or using some alphabet, he pointed out that you could, in theory, write code for this machine to solve any problem out there. And so Turing complete means that any set of inputs can be used to produce any outputs. Alan Turing, what a guy. There's been movies made about him, books made about him. Yeah, so we can never meet Mr. Alan Turing. You know, we can never say thank you to him. But, for what it's worth, just want to say here on a little YouTube video, Mr. Alan Turing, thanks mate, you were amazing.